Hello friends, today we are going to solve a 1D transient heat conduction problem with convection boundary conditions in Cartesian coordinates using FTCS or forward time centered space finite difference method. Our objectives are to present a simple 1D transient heat conduction problem. We have convection boundary conditions at the ends. We will discretize the domain into say 5 grid spacings. We will consider two time steps and solve the problem using FTCS finite difference method. We then vary grid spacings and time steps and obtain solutions. Our problem is shown here. We have a 0.1 meter long copper bar. The initial temperature of the bar is kept at 0 degrees Celsius. Alpha and K are the material properties of the bar. Alpha is the thermal diffusivity, which equals 1 e to the negative 4 meter square per second. K is the thermal conductivity and is equal to 386 watts per meter degree Celsius. At one end of the bar, the convection conditions are given as follows. Here H1 is the convection heat transfer coefficient, which is equal to 70 watts per meter square Celsius. The ambient temperature at end 1 is T-inf1, which is equal to 200 degrees Celsius. H2 is the convection heat transfer coefficient at the other end, which is equal to 30 watts per meter square Celsius. The ambient temperature T infinity 2 equals 100 degrees Celsius. The general heat conduction equation in 3D Cartesian coordinates is given as dou square T over dou x square plus dou square T over dou y square plus dou square T over dou z square plus G over K equals 1 over alpha times dou T over dou T. Here T represents the temperature in the domain and T is a function of x, y, z, the spatial coordinates, and the lowercase t, which represents time in seconds. Alpha is the material property called thermal diffusivity and is given in meter square per second. Alpha equals K over rho C. Here K is the thermal conductivity of the material in watts per meter Kelvin, rho is the density of the material in kilograms per meter cube, C is the specific heat capacity of the material in joules per kilogram Kelvin, and G is the volumetric rate of internal heat generation in watts per meter cube. We assume that the material thermal conductivity is homogeneous and isotropic in the medium. Accordingly, the thermal conductivity is uniform over the entire medium. For 1D transient heat conduction with no heat generation, equation 1 reduces to a simpler form. We assume that the temperature does not vary significantly along y and z directions when compared with x direction. In other words, we have insulated boundary conditions along the y and z directions. Also, there is no heat generation term involved, so G equals 0. Accordingly, we get dou square T over dou x square equals 1 over alpha times dou T over dou T, and T is a function of x and t. This equation is rearranged as dou T over dou T equals alpha times dou square T over dou x square. The initial condition is given as T at x comma t equals 0 equals Tn. The boundary conditions at t at x equals 0 comma t, we have convection boundary conditions. As we discussed before, we have the values for h1 and t infinity 1, which are basically the convection heat transfer coefficient at the end 1, and T infinity 1 represents the medium or the ambient temperature at the end 1. Likewise, at the other end, T at x equals L comma T, the boundary conditions are H2 and T infinity 2. Here H2 is the convection heat transfer coefficient at the end 2 and T infinity 2 represents the ambient temperature at N2. To obtain the temperature profile, we need to solve the above PDE. We will utilize finite difference method to solve the above PDE. To do so, we need to replace the partial derivatives with finite difference approximations. We will replace the time derivative with first order forward difference and the space derivative with centered difference approximations. Accordingly, we get Tin plus 1 minus Tin over delta T equals alpha times Ti minus 1 n minus 2 times Tin plus Ti plus 1 n over delta x squared. Rearranging, we get Tin plus 1 equals Tin plus alpha delta T over delta x squared times Ti minus 1 n minus 2 times Tin plus Ti plus 1 n. Let D equals alpha times delta T over delta x squared, where D is the diffusion number. We then get Tin plus 1 equals Tin plus D times Ti minus 1 n minus 2 times Tin plus Ti plus 1 n. Equation 5 is the finite difference approximation of the original PDE which we are trying to solve. That is the partial differential equation. Here I represents the node location on the discretized domain and n represents the time step. The finite difference stencil is given below. The above approximation is called forward time centered space or FTCS method. This is an explicit method. Hence, temperatures Ti's at future times n plus 1 can be directly obtained based on Ti's at present times as shown in equation 5. Explicit methods are conditionally stable. The stability criteria for this type of problem is given as F4 times Bi plus 1 should be lesser than or equal to 0.5. Here Bi represents the Biot number, which is equal to h times delta x over k, and F4 represents the Fourier number, which equals alpha times delta t over delta x squared. Also, diffusion number / delta t need to be smaller based on the accuracy desired. Please also note that we have used diffusion number before and d equals Fourier number. The error is of the order of delta t plus the order of delta x squared. Now let us discretize the 1D domain into, say, 5 segments or grid spacings, equally spaced as shown below. Note that temperatures at node 1 and node 6 are not fixed as in the Dirichlet boundary conditions, but we have convection BCs at nodes 1 and 6. To apply node equation 5, we need to consider the interior nodes 2 to 5. Accordingly, let I equals 2 and n equals 0. Equation 5 becomes T21 equals T20 plus D times T10 minus 2 times D20 plus T30. Similarly, we can get equations for I equals 3, 4, 5 and n equals 0 as shown here. The convection boundary conditions is represented here. For example, at the right side of the boundary where n equals 6, assume the heat transfer coefficient is h and the medium temperature or the ambient temperature is T infinity. So we have to consider a grid spacing which is half of delta x, that is delta x by 2. So to solve this temperature at this end, we have to apply an energy balance. Accordingly, the convection, the energy coming from one end by convection, for example, is equal to the energy increase in the plate for this particular region, delta x by 2, there is increase in energy, and there is a heat flux going from, for example, n to 5. So accordingly it is represented as minus k times a times dou t over dou x plus h times a times t infinity times Tn0 equals rho times c times delta x over 2 times a times dou t over dou t as equation 6. Here we are assuming thus that T infinity is greater than Tn. In other words, the ambient temperature at that boundary is greater than the initial temperature at node n. So we can rearrange this equation further as 7, and we can do some further rearrangement. Here note that we are representing dou t over dou x as Tn0 minus Tn minus 1 0 over delta x. This is the finite difference approximation of dou t over dou x. Likewise, the finite difference approximation for dou t over dou t is Tn1 minus Tn0 over delta t. So we are using first order approximations here. When we do this, we get an equation as shown in equation 8. Please note that whenever there is a convection boundary at one end, it's a little more complicated than a Newman boundary condition or a Dirichlet boundary condition when we keep the temperatures fixed at one end or if there's a constant flux at one end. So when we use this equation 8 we derived, which is a general equation for any boundary node, into our node at the left hand side, node 1, we get equation 9, that is minus k times a times dou t over dou x plus h1 times a times t infinity 1 minus t1 equals rho times c times delta x over 2 times a times dou t over dou t. And following the same procedure, we get T11 equals F4 times 2 times Bi1 times T infinity 1 plus 2 times T20 plus 1 over F4 minus 2 times Bi1 minus 2 times T10. Here, as we mentioned before, F4 is the Fourier number, Bi1 is the Biot number at close to node 1, and T infinity 1 is the ambient temperature at close to node 1. And T10, for example, is the initial temperature at node 1. Likewise, we can solve for the temperature at the other boundary node, Tn, for the next step, for the first step. That is Tn1 equals T61 equals Fourier number times 2 times Bi2 times T infinity 2 plus 2 times Tf0 plus 1 over Fourier number minus 2 times Bi2 minus 2 times T60. Let us assume a small time step delta t equals 0.4 seconds. We have delta x equals L over m, which is m represents the number of grid spacings, which is equal to 0.1 over 5 equals 0.02 m meters. We have to use smaller delta values if we need higher accuracy. The Fourier number and the Biot number at both ends are calculated. The numbers are shown here. So we also have to verify if we meet the stability criteria. As we mentioned before, F4 times BI max, which is the maximum of BI1 or BI2 plus 1. This value is obtained as 0.1003, which is lesser than 0.5. So we meet the stability criteria here. Now we substitute the values of D/F4, BI and the initial conditions into the previous equations. We get T11 equals 0.1451 degrees Celsius and T61 equals 0.031 degrees Celsius. These are the temperatures at the boundaries, at both boundaries for the first step. So now we need to calculate the temperatures at the interior nodes for the first time step. And the equations we already derived are given here. So substituting the values of T20, the initial conditions basically, we get the temperature profile for the interior domain, or the temperatures at all the nodes for the first time step, and is given as shown here. We follow a similar procedure for the second time step. We find the boundary temperatures at both ends, and we find the interior node temperatures. And the temperature profile for the second time step is given here. Likewise, you can find the temperatures at this interior as well as the boundary nodes for the next time step by choosing n equals 2 and so on. We will present graphical results using MATLAB. By using MATLAB or suitable software, you can develop a course for a general case where the number of grid spacings and time steps can be altered as desired, and the solutions obtained accordingly. We will now go to the MATLAB program we developed for this case. Here we have the thermal diffusivity alpha specified and the thermal conductivity specified. H1, the convection heat transfer coefficient, and the medium or the ambient temperature at end 1 is specified. And the left hand end is specified. Likewise, the convection heat transfer coefficient and the temperature at the right end is specified. The total time is considered as 4 seconds and the number of time steps as 10. So our delta t, or the time step, is 0.4 seconds. We have x length equals 0.1 meter. We use y length equals x length for graphical purposes. Also, nx equals 5. There is a number of spatial grids in the x direction. So delta x equals 0.1 over 5, which is equal to 0.02 meters. And we'll run this program. T at step 1 is shown here, and T at step 2. Step 1 is basically the initial condition, and step 2 is the first step here. And we can compare the values to the ones we have in the presentation, and they seem to match 0.1451 at one end and 0.031 at the other end. The interior temperature, nodal temperatures are 0 degrees Celsius. And we'll look at the temperatures for the second time step as well. So 0.2611, 0.0145 at one end, and followed by two zeros, and then 0.0031 and 0.0558. So we obtained the same temperatures by developing a program here. So let's look at the graphs here. So at the top left hand side we have the initial conditions. The whole domain is at 0 degrees Celsius. At the bottom left hand side we have the final temperature distribution when time equals 4 seconds. On the right hand side we have the animation. It's now, since it's a short time, total time of 4 seconds, the animation is done. We'll go back and change our parameters here. For example, let's keep the total time as 100 seconds, a number of time steps as 1000, and we'll increase the total number of spatial grids in next to 20 from 5. We'll run this again. Now the initial temperatures again is shown at the top left hand side. When time equals 0 seconds, we have temperature equals 0 all over the domain. At the bottom left hand side we have the final temperature distribution when time equals 100 seconds, and we can see the changing temperature profile with time on the right hand side. To reiterate, we have convection conditions at both ends. At the left end we have H1 equals 70 units and T infinity 1 equals 200 degrees Celsius, and at the right hand side H2 equals 30 units and T infinity 2 equals 100 degrees Celsius. So the temperatures are climbing at either ends. The initial temperature is 0 degrees Celsius. This will continue till time t equals 100 seconds. So we will now go back to our PowerPoint. To summarize, we presented a 1D transient heat conduction problem with convection boundary conditions at either ends. We discretized our domain and solved the problem using finite difference method. We used the FTCS or forward time-centered space finite difference method. We varied the grid spacings and time steps, solved the problem, and presented the result.